Thank you for the introduction, and also thanks very much for the invitation to speak. I will speak on two projects with these collaborators. One project is on we call it the topological twist of massive SQCD together with Johannes Assmann and Elias Furr, and a project titled Path Integral Derivations of K-theoretic Donaldson invariants together with Greg Moore, Hyun Kim, who is here, Xinyu Zhang, and Runkai Tao. Okay, so these projects are slightly different directions, but I will talk on the aspects where they kind of come together. So just as a very general introduction, correlation functions are at the heart of quantum field theory. And it's a large effort to include all perturbative and non-perturbative effects and to increase the numbers of insertions to as high as possible. There's a motivation to study this in maybe idealized theories where we can address these questions. And one set of theories are correlation functions of the supersymmetric theories n equals 2 and n equals 4 Young-Mills, in particular those which are topologically twisted and considered on a compact Four manifold. There's a lot of interesting physics going on in the sense that many of these observables feature many crucial non-perturbative phenomena in Young-Mills theory. And at the same time, they provide deep connections to the geometry of Four manifolds and incidental moduli spaces, as well as to analytic number theory, so giving an interesting interplay between the math and physics. To be a bit more detailed, these correlation functions involve usually topological invariants of the Four manifolds, and there are many of them. The classic maybe Donaldson-Witten invariants, the Seiberg-Witten invariants, Waffa-Witten invariants, and the relevant for this talk, the so-called Sager numbers and K-theoretic Donaldson invariants. So we are interested to calculate the physical path integral on a compact smooth Four manifold X, and as a result, the path integral is a functional integral over all the fields of the theory. And there's a specific family of Four manifolds where there is a lot of kind of physics goes into the analysis. Those are Four manifolds with B2 plus X is 1. Since there is a non-trivial contribution from the Coulomb branch of the theory, and basically the full solution of these theories is required in order to evaluate the path integrals. So this actually has motivated to kind of further study these Coulomb branches, in particular the effective couplings for the Coulomb branches in the case of for now rank 1 theories. So in the first couple minutes, I will just focus on the Coulomb branches of the theories for these two cases, the massive SQCD and the 5D theory compactified on X times S1. Okay, so let us start with the very kind of classical case. If in the case of n equals 2 supersymmetry with SU2 Gates groups and no hypermultiplets, then the Gates group is potentially broken by a web of the vector multiplet scalar, can be brought to this diagonal form, and there is a classical Gates invariant order parameter, which then equals 2a squared. And this, the expectation value of u, or features in the effective coupling constant. We choose the convention here that tau is theta over 4 pi plus 4 pi over g squared. And then the first term is 4i over pi log of a over the scale lambda. All right. Now it's the famous Seiberg-Witten solution gives all the subleading terms in this expansion by formulating the effective coupling as a complex structure of an elliptic curve. I've written the elliptic curve here, and A is then famously a contour integral of the Seiberg-Witten differential. And then U can be expressed in terms of a Jacobi theta series in this form. Okay. And we use the notation that Q is e to the 2 pi I tau, and theta j are the Jacobi theta series. Okay, now this theory has two strong coupling singularities for when U is equal to plus or minus lambda squared, where a monopole and a dione become massless. And then the monodromies around these, the weak coupling point and these singularities, they generate the so-called congruent subgroup comma not 4. And this group leaves the parameter U invariant. So if you make this transformation of tau to A tau plus B over C tau plus D, it is equals U of tau. And this congruent subgroup is the following subgroup of SL to Z, namely the subgroup where B is equal to 0 modulo 4. Okay. And A, C, and D are integers. Okay. So we can make plots of the domains. Here I've plotted the domain in U space. And we have the two singularities where U is equal to minus lambda squared and plus lambda squared. And we can make a plot in tau space. This is the space in tau space, the upper half plane. The fundamental domain for SL to Z is usually taken to be this keyhole fundamental domain. Since gamma not 4 is a smaller group, we get a larger fundamental domain, and it consists of these the union of these 6 images of the keyhole fundamental domain. Okay. The singularities, these two monopole and dione singularity correspond to these cusps at the bottom, and then recoupling is the tau to I infinity limit. And further, we have these identification between this side and this side, and this side and this side, this side and that side, and this with that arc. And you can see on this side then the images of all these keyhole fundamental domains. This keyhole fundamental domain is this part. S is the neighborhood of the monopole singularity, etc. for the other domains. Okay. Okay. There's a similar story for if we add hypermultiplets in the fundamental representation. Then if we add a mass for this hypermultiplet, we get the first few terms in the expansion for tau. So there is, in addition, this term we already saw for NF is 0 case. Now for NF is 1, there are these two terms due to the hypermultiplet, which add to the first term. And then there are further subleading corrections. Okay. If the mass is equal to 0, then we can combine all these terms, and this 4 will become a free. And we see that then we get a width-free fundamental domain. And we get free cusps at the near the strong coupling. This is again the monopole singularity. This is the dione. And then there's an extra singularity when the hypermultiplet becomes massless. And we get also the diagram then in the U plane. We have these free singularities which are invariant under Z-free rotation, and we again can identify all the images. But this is in the case when the theory is massless, and one can determine U as a function of modular forms. There's this function, the square root of E4 over the third root of E4 to the power 3 over 2 minus E6. If you expand it, you get a series like this, which is indeed has powers whose exponents are fractions of 3. But it's important to note that now the U is expressed in terms of square roots of modular forms, and these are in general not modular forms, because if you take the square root, then if the faces don't match up, then it does not satisfy the transformation properties of a modular form. One can verify, though, that it's left invariant under the path transformations, with which I mean that you go, say you decide to go from, you start here, you go down, go around this cusp, and go back up. You can show invariance under those sequence of transformations, but it is not invariant under a subgroup of SL2Z. Okay. So as a result, U is now not a holomorphic function of tau on the upper half plane, but there are branch points at tau equal to pi I over 3 modulo Z. So those are these points here. And that's where E4 vanishes. So as I said, that the domain is not of the form H mod gamma for some congruent subgroup, but we can make a fundamental domain by just requiring that tau is the same as, is equivalent to tau prime in the upper half plane if U is equal to U of tau prime. So that's you still can have a notion of fundamental domains for these order parameters. Okay, now in general, to determine U, say if you want to go away from this massless point, we use the Weierstrass form, which we also saw in the previous talk. Then there's a formula for the J function in terms of these coefficients G2 and G3. And we can rewrite that equation in terms of, in the following form, we get G2 cubed minus 27 G3 squared times J minus 12 cubed times G2 cubed. And then if this polynomial is equal to 0 with x replaced by U, that's then the U has to solve that equation. So this at the U is the root of this polynomial. And we see it as an order 6 equation, and that's why we saw these, in agreement with these 6 images we saw in the fundamental domain, because J is itself a function on the F1 or on the fundamental domain for SL2Z. Okay. So in general, for general, say NF and general masses, there won't be an explicit solution. And it is important to note that there are, in general, branch points where 2 or more J-dependent roots of P and F coincide for a specific value of J. So that's what happens in particular if we increase the mass, take a non-vanishing mass. Then the branch points I was discussing, we first had the branch points in each of these points, but that was due to the identification between this side and this side. There are only 2 branch points, which then start to move in along these arcs if we start increasing the mass. So these branch points start to move in the interior of this fundamental domain. And that's the effect of turning on the masses. So you can see the effect here also. If the branch points move in, there is a branch cut from this point to the branch point. And now the bottom of this arc is identified with the bottom of this arc, and the top of the arc is identified with the top of this arc. So you see that here is you have a single green and this orange one. Okay. So if we increase the mass further, then once we reach, at some point we will reach the so-called Argyris-Douglas mass. That's when these 2 branch points, they coincide on this point. So we have here the Argyris-Douglas coupling, and then we see, because this part was identified with this part, that actually these 2 domains have completely decoupled from the rest of the domain. The backward? Oh, x is the variable for this polynomial. Yeah, yeah. And we substitute U in this. U is a solution to the roots of this, to the vanishing locus of this equation. And there are six solutions for a given J. And that then gives us the six copies here. Okay, so these two images of F are disconnected from the domain, and we get the following picture for the U-plane, where we have one singularity at the AD point, and then still the singularity at this monopole cusp. And you can consider the zoomed-in theory, the AD of the theory, that has its own curve. And if you consider the order parameter for that curve, you can check that actually corresponds to the union of these two elements. So you see kind of naturally this splitting happening between the AD theory and the parent theory. Okay, I won't go into too much detail for this talk about the AD theory. So let me move on by tuning the mass to a larger mass. Then one branch point will continue along this arc going in, and this one will start going up. Okay. So then it's actually natural to bring this arc, move it here to actually move this one to the middle, such that this arc, this one is moved to the middle, and this one will move to the side, and then we get a curve like this. And then if we continue increasing the mass, then these branch points will move up, and we reproduce the domain of the pure theory. So you see that in the infinite mass limit, we reproduce the pure theory. So there is, in a sense, really a smooth transition from the massless curve to the infinite mass curve. Well, a priori, this, at least to us, this was not clear, because the duality groups is a really kind of discrete notion. But we see with the branch points, there's a smooth transition between these curves. Okay. Any questions so far? Okay, so now I would like to say something about the 5D theory. The theory on R4 times S1. That's the other project. So we'll consider first the theory on a circle of radius R. The 5D theory, just to recap a little bit, has a gauge field AM and a real scalar sigma, and it has the following global symmetries: an SU2R symmetry, then a U1 instanton symmetry, and a U1 Kaluza-Klein symmetry from the circle reduction. The U1 instanton symmetry is a rather novel symmetry whose current is in a sense the instanton current. It's the trace of F wedge F in the Hodge star of that. And the particles with this charge are then called instanton particles. We have the usual supersymmetric kinetic action like this, and we can add a Chern-Simons term to the theory, say with a coefficient kappa. And we can also, what will be relevant for us, to weakly gauge this global symmetry U1I by considering it as a so-called frozen vector multiplet, for which we can tune on a constant vacuum expectation values for the AI and sigma I. Then we can consider a mixed Chern-Simons term for this multiplet and the kind of dynamical vector multiplet. So of this form, we have an Fi wedged the 3D Chern-Simons action, and there's also plus the other terms to make it supersymmetric. And one of the terms to make it supersymmetric is this term sigma I trace F wedge star F, and we see if we compare with this term, that this is just the term of the kinetic action. And in fact, the kinetic or the standard Young-Mills action appears as part of the mixed Chern-Simons action. If you make this identification that the WEF of sigma I is minus 8 pi squared over G5 d squared. And we will later on then include a flux n for this instanton, a background flux for this instanton gauge field. Okay, there are various parameters at play here. We have if you want to think of it as a theory in 4D, we have a 4D scale lambda, and S1 has radius r. We can combine them to a dimensionless parameter curly r, lambda times r, and this is also gives encodes the 5D Young-Mills coupling, e to the minus g pi squared times r over g5D Young-Mills squared. And we have various electric PPS particles for gauge group SU2. We have W bosons with mass Ma is 2 times the local parameter A, which now is the integral of sigma plus I times A5 over the circle, over the 5th dimension. We have the instanton particle, which has complexified mass Mi 1 over r times log of r to the 4, curly r to the 4. And we have Kaluza-Klein momenta with the complexified mass 2 pi I times r. Okay. We also have, you can express these quantities in terms of the prepotential, which is expressed in terms of the Li freeze, and log r actually can be written. And then there are further subleading terms, and the subleading terms also include a dependence on kappa. So if you on the Chern-Simons coupling, this Chern-Simons coupling will feature in the prepotential. Okay, and then we have periods for the dual magnetic objects. For the monopole is dF dA, for the dion is dF dMi, and for the Kaluza-Klein dF dMk. Now the order parameter for this theory is the Wilson line operator, where we integrate sigma plus I A5 over S1. The first terms are e to the RA plus e to the minus RA, and then there are further corrections. Okay, so let's look a little bit more into the solution of this theory. We will concentrate on the theory for kappa is equal to 0. Then the curve follows from these equations. And we have four singularities, namely where u is equal to plus or minus 2 times r squared plus or minus 1. So I've plotted here in the plane. So these are these points. You have massless particles corresponding to basically 4 charges. These are electric PPS objects and the mass of the monopole. So they span a 4-dimensional lattice, and they're generators of that lattice in a sense. One can show that they vanish on these singularities. This is the usual monopole and dion, and then these are monopole and dion, and plus the instanton charge. Now it's useful to again try to understand this in terms of the effective coupling. Using the theory of elliptic curves, one can demonstrate that u squared is equals to this the sum of these 3 terms on the right hand side minus 8 times curly r squared times u. This is actually a straight u, just to distinguish it a little bit from the previous u, which was dimension-full. This one is the dimensionless, plus 4r to the 4 plus 4. And u is then this expression in terms of the Jacobi theta series. It's basically equal to the expression we saw before, except that this one is dimensionless. Now we see that this is we have u squared here, so we get a double cover of the fundamental domain for the pure theory. Okay, so that's what we see here. We get two copies of the fundamental domain for the pure theory next to each other. But there is a branch point here where u is equal to 0, which is plotted here in the domain. There we get a branch cut, which we take to go up to infinity. So these two copies, they talk to each other through the branch cut. This line is identified with the left of this line, and the right is identified with this one. U changes sign over this line, but here we also have that the right of this branch cut is identified with the left of this branch cut, and the right with the left. So that's where they are attached to each other. Okay. Yeah, and if you take the radius to be very small, these branch cuts move up. It's also interesting to rearrange this domain a little bit, and then you can bring it to this form. And now if r goes to 1, then these points will go down, and you'll find that you get that then the square root actually factors, or the argument factors, and you get a modular form for gamma not 8, maybe of a congruence of gamma not 8. So these type of domains were also studied by Closet and Magurenu in 2021. Any questions? Okay. Okay. There are no questions. Okay. Let's then continue and consider move on to form manifolds and formulating these theories on a form manifold and evaluating their path integrals. So just to recap and introduce a notation for form manifolds, the second cohomology naturally comes with an intersection form B, which I denote by B. It's the integral of x over k1 where it's k2. Gives rise to an integral unimodular lattice L, which is the image of H2xz in H2xr to treat potential torsion properly. This lattice has signature B2 plus, B2 minus, and in order to get non-vanishing correlators of these theories, we need that B2 plus B1 is an odd number. And basically for simplicity, we restrict to the case that B1 is equal to 0, or simply connected form manifold. As I mentioned, the form manifolds with B2 plus is 1 are special in the sense that they involve more physics. And an important parameter is then this J, which is the normalized generator of the unique self-dual direction H2xr, which is dependent on the metric. The self-duality depends on the metric. So this parameter depends on the metric, and we'll see that the partition functions, that metric dependence kind of features in the partition function for this parameter. And at the same time, it provides then a projection of K of a lattice vector to the positive and negative definite lattices by taking the inner product. Now we first assume that X is spin, such that we have a chiral SU2 spin bundle, that it is a well-defined chiral SU2 spin bundle. Then the so-called Donaldson-Witten twist is the one we will consider to formulate the theories. We replace SU2 plus, the SU2 plus representation by that of the diagonally embedded subgroup of SU2 plus times SU2R. Then one of the supercharges will become a scalar, or at least one, and we can consider cohomology with respect to that scalar supercharge. So in this case, the fields of the vector multiplet, the scalar phi and a mu, they remain a vector and a scalar, but hypermultiplets scalars, they become space-time spinners, m alpha dot and mr alpha dot. So that was one reason to restrict here to a spin manifold, but we like to do more, be more general and formulate the theory on a non-spin manifold. So to do that, we need to couple the hypermultiplet to a so-called spin C line bundle L, such that S plus times the square root of L is well defined as a spin C bundle. Okay, so if X is not spin, then S plus is not well defined, and the square root of L is not well defined, but their product is well defined, to say it a bit heuristically. Okay. And if there are canonically determined spin C structures, if you take a canonically determined spin C structure for L, then the W plus is then the sum of lambda of 0 forms plus 0,2 forms on the complex or almost complex manifold, and W minus corresponds to the 0,1 forms. Almost complex structure. You can formulate this on an almost complex form manifolds. But there's an infinite family of spin C bundles you can choose in order to get well-defined W plus. A little recap on basically on Donaldson theory and the interpretation in physics. You can introduce observables in Q cohomology. One observable is the so-called zero observable, which is basically the order parameter of the theory on the Coulomb branch. And we can also introduce a surface observable, O2, which takes this form. And they have the property that they are annihilated by Q, but they are not Q exact. And their correlation function this is for the pure SU2 theory. If you calculate their correlation function, we get a generating function of this variable p and x, and the coefficients are the Donaldson invariants, which are introduced by Donaldson as integrations of special differential forms on the moduli space of instantons. So omega u is a 4 form, omega I is a 2 form, and these intersection numbers then gives us these Donaldson invariants. Any questions? Yes. Sorry, a line. Yeah, there can be a line operator, except that we are restricting to form manifolds with B1 is 0, and then they will because we don't have any one-dimensional cohomology, their expectation value would vanish. But if you have indeed form manifolds with one cycles, you would also introduce those in the theory. Other questions? Okay. Okay. Now, if we evaluate the path integrals, schematically, it takes the following form. We get a contribution, a so-called U-plane contribution for some observable O, and then we get a so-called Seiberg-Witten contribution, where the Seiberg-Witten contribution for the pure theory has delta function support on the strong coupling cusps where U is equal to plus or minus 1 or plus or minus lambda squared. What I hinted at before, that the part for the contribution from the U-plane is only non-vanishing for B2 plus smaller equal to 1. Actually, the B2 plus is 0 case has been still poorly understood. So we will restrict to the B2 plus is 1 case. And where this contribution becomes an integral over the Coulomb branch, and therefore actually becomes a testing ground for the analysis of the Coulomb branch. And in this case, the path integral reduces to an integral over 0 modes, where a mu phi 0 is equal to a, and the fermions eta, psi, and chi naught. Okay. So the integral takes the following schematic form. The SU2 is broken to U1, so we get a sum over fluxes of the unbroken U1 Gates group. And then then we get the following integral. These are the remaining fields to integrate over. We get topological couplings A and B, and then the exponentiated action, which can all be evaluated to this form. And we have now changed variables from A to tau. So that's why I spent some time discussing the reparametrization of the columbrans in terms of the effective coupling for this change of variables, essentially. Then nu is this basically the measure. This comes from the Jacobian, and this is the sum over fluxes, fluxes k. And this mu is the so-called 't Hooft flux, which is the trace of f of the Gates bundle. Any questions? Okay, so I won't go into too much detail here, but in the last few years, there's been realized that it's possible to evaluate these integrals efficiently using mock modular forms for all x with b2 plus equal to 1. Basically, the idea is as follows, that using the theory of mock modular forms, we construct a suitable antiderivative of the sum over fluxes. This antiderivative is a function of tau and tau bar, but it has a natural holomorphic part. And then this contribution of the U-plane evaluates to the constant term of the holomorphic part of these three terms. O is the observable, the measure nu, and then the holomorphic part f of f hat. Okay. Then to get back to the form of the partition functions I mentioned, it's the form of the U-plane plus form of Seiberg-Witten contributions. The Seiberg-Witten contributions, in general, they are supported on all the strong coupling cusps. So 2 plus NF in the case of NF flavors. And they have a following form that they involve, again, topological couplings curly A, curly B. And then they are determined in terms of the so-called Seiberg-Witten invariants, which are numerical invariants, which then multiply other terms which depend on C, the argument of the Seiberg-Witten invariant, which is itself a spin C class or spin C structure. And using the phenomenon of wall crossing, it's possible to actually deduce these Seiberg-Witten invariants from the U-plane, and then actually generalize this for manifolds with B2 plus larger than 1. So essentially you can get the full result from the U-plane integral, except for the values of the Seiberg-Witten invariants themselves. Okay. Any questions? Okay, that was a bit the general picture. Let us then go back to the SQCD. Their Q-fixed equations are the so-called non-abelian Seiberg-Witten equations. These are this form. So we have, this is the self-dual part of F, and then we have a term involving the scalar, it's the twisted scalar fields of the hypermultiplet. TA is in the representation of the hypermultiplet, and we have this Dirac equation. Equations are invariant under U1 flavor symmetry, or U1 to the NF in the general case, where we rotate these monopole fields. If X is non-spin, then we need to couple to a spin C structure, because we still wrote those in terms of spinners. Okay. Now with this symmetry, we can localize to the fixed points of this symmetry, which gives us two components. One is the instanton component, when these m's are equal to 0. When the m is equal to 0, we just get the self-duality equation or the instanton equation. And then a abelian component where f is diagonal and m alpha dot is strictly upper or lower triangular for SU2. Now we can show with a similar spirit, as in the case of the Donaldson invariance, that if we calculate a correlation function for this theory, there is an insertion of the Euler character of the co-kernel of the Dirac operator, and then this is multiplied by the differential form corresponding to this observable. And if we localize with respect to this U1 symmetry, one will divide by the Euler character of the kernel of D bar D slash, such that we get the index bundle WK, and we get Chern classes of the index bundle of the Dirac equation of the Dirac operator. So then we get the following form: the Chern classes are equivariant. So we get where the equivariant parameter is the mass m. We get the following expansions: m to the power the rank of WK, and CL to the ML times the observable differential form for the observable. And this is the contribution from the instanton branch, and this from the abelian or monopole branch. We can see that both limits are interesting. M to infinity, then only L is 0 contributes, and we are back to the Donaldson invariance. Whereas if M goes to 0, then only the top Chern class contributes. And if there are no observables, we get an Euler type number from the correlation functions. And I should add that a bit recently, the mathematicians call these intersection numbers Segre numbers, even though we are integrating Chern classes. But in some sense, Segre classes defined in intersection theory are more fundamental than Chern classes. So it's also appropriate to call them Segre numbers. Okay, so let me then proceed and mention some explicit results. First, the form manifold P2. It has P2 is equal to B2 plus is equal to 1. It's a non-spin manifold, and its Seiberg-Witten invariance vanishes. As a result, the U-plane gives the full results of these correlation functions, and we get tables like this. This is for an F is 1. We see this is here on the vertical down, we get L is 0, 1, 2, 3, 4, which is the power of U to the L inserted in the, so this is correlation functions of U to the L. And the experts may recognize the values of the Donaldson invariance, this 19 over 2 to the 6 and 85 over 2 to the 9. But we get also numbers where the Donaldson invariance vanishes, and we get subleading terms here. And we see that here for an FS2, that's also happening, that we get subleading terms. I've written it maybe in a bit of difficult form, m to the 6 over m to the 4 here, for example, but this is to clarify the data in this table. M to the 6 is from this term, the virtual rank of the index bundle is usually negative. So, so this means that the rank of the index bundle is minus 6 on the other slide. And we are integrating the 4th Chern class because we have CL over m to the L. That's why we use this a little bit rich notation here, but it's to indicate the rank of the index bundle and the Chern class, which gives the non-vanishing type. Okay. Any questions? Okay, so here I took het hoofdflux equal to 1/2. The theory is not well defined for het hoofdflux equal to 0 if you don't turn on background fluxes. So this is for vanishing background fluxes. And I should also say that this result is the same if we do the calculation for a large or a small mass. So we saw these very different domains in the first half of the talk. And if you integrate over the domain for large mass or the domain for small mass, we produce the same numbers. Okay. And these are then tables for if we turn on background fluxes. So this is for phi 0. If the hoofdflux is equal to 0, we need a half integer background flux. for the one-form symmetry or for the U1 gauge field, and we get these numbers. And this is then background fluxes for phi 1/2. Okay. And now let me also give some results for another manifold K3. Sorry, this should be K3. Then B2 is equal to 22. B2 plus is equal to 3. This means that the U-plane does not contribute. It's a spin manifold, and the only non-vanishing Seibert-Witten invariant is equal to 1 for C is equal to 0. Then for vanishing background fluxes, we get a table like this. So you can see finite polynomials for each value of L, corresponding to U to the L. And this is a sum of 3 strong coupling singularities, U1 star, U2 star, and U3 star for the NFS1 theory. Okay. But this U1 star and U2 star, so it's striking that we get these finite polynomials, which indicates that we have proper vector bundles over the moduli space of Q-fixed equations. At the same time, the combination of U1 star and U2 star corresponds to the instanton moduli space. So if we single out the contribution of these two singularities, we get actually infinite series. Okay. And now these numbers here, they reproduce the Sergei numbers for K3, as for example studied by Götze, Kohl, Götze and Oberdick mathematicians. They actually reproduce their universal functions. So this is more, also for other manifolds, we would match the results of these papers. And here the understanding that we get an infinite series now suggests that if we restrict to the instant moduli space, the bundle is rather a sheaf for which the Chern classes are not, they run all the way to the dimension of the manifold. This is a sum of the free cusps. These two give the UV contribution of the instanton branch, and this is then the contribution from the monopole branch. So if I just consider the contribution of these two cusps, I get these series, and the third monopole branch is precisely such that it kind of cancels all these contributions. So it might be a motivation for mathematicians to consider the monopole branch for this theory and also calculate intersection numbers on those monopole branches. Okay. Any other questions? Okay. Let us then, in the remainder of the time, I move on to the 5D theory. Where we consider the 5D theory on a 4-manifold X times S1. There are, in a sense, two approaches one can take. You can reduce to the circle, and you get a supersymmetric sigma model with target space, the moduli space of instantons. And from this perspective, then using collective coordinate approach, one can show that the partition function becomes a sum of indices of the Dirac operator with expansion parameter, this dimensionless R to the 4K, or the dimension of the moduli space. So this R was the radius of the circle times the 4D scale lambda. And more generally, since we turned on a flux for the U1 instanton symmetry, this will induce a bundle over the instanton moduli space, and you insert e to the this is then the Chern class basically of that line bundle over the moduli space, or the image of the Donaldson map of this 4-dimensional 2-4. Any questions? And if X is complex or in algebraic geometry, one can tensor this line bundle with another line bundle and then relate it to the so-called holomorphic Euler characteristic by relating A hat to the Todd class. Okay. Now on a toric manifold, we can localize with respect to a C star action. So in the physical approach, then we can bring the partition function to the following form with an integral over an auxiliary field h, and an integral over the local coordinates a and a bar. You get a further argument like this, dA bar g of function of a and a bar and h. And this can be expressed in terms of Nekrasov's partition function on R4, a product over the number of patches of the toric manifold. Sorry? N is this background flux. Sometimes I called it Ni. So sorry if it's confusing. This is the background flux for the U1I field.
It's H.
H is an auxiliary field of the. Yeah. Okay, in this way we can derive a wall crossing formula so that the difference of, sorry, this would be a minus, otherwise it's 0, obviously. So the difference of two partition functions for different choices of j plus and j minus, then becomes the following form. The 8 is from the width of the domain we saw in the beginning for the fundamental domain in tau space. Then we have again terms which are very similar to what we saw before. We have the measure nu, coupling to the background flux c, and then an infinite theta series. This is the expression for nu. V is this function of the prepotential, and C is this function. And to evaluate it, one first makes a series in R, and then picks up the q to the 0th term. Okay. Yeah, this indefinite theta series is an example of a mock modular form. I won't go into details here, but you can look at the references. Okay. Now, alternatively, we can reduce to 4 dimensions, where we can carry out the U-plane integral. Then the U-plane integral takes also a form similar to what we saw before. It is this measure nu, c to the n squared, and the sum over fluxes psi, which then involve these couplings to the background flux. And this leads to the same wall crossing formula. And we can also evaluate it for the 4 manifolds, such as P2 or K3. For P2, we get series expansions like this, which are in agreement with results of Gutsche, Nakajima, and Yoshieko from 2006. And it is 0 for the even n. And if we take a vanishing and hoofd flux with coupling n, we get series expansions like this, which are again in agreement with the paper of Gutsche, Nakajima, Yoshioka, except for this first term, which we attribute to singularities due to reducible or strictly semi-stable bundles. Okay. Okay. And we can extend to manifolds with B2 plus larger than 3. Sorry, there should be a plus there. Then we get, and we can evaluate those functions I was kind of showing you before, the curly A, the curly B, curly E. If we do that, then we arrive at a series like this, which then reproduces results of the K-theoretic Donaldson invariance by Gutsche, and Williams from 2019. So that brings me to the end of the talk. Just to conclude, we have explicitly evaluated, analyzed the partition functions and correlation functions of the n=2 theory, the fundamental matter with generic masses, and the 5D n=1 theory on x times S1, also for SU2 Gates group. One message to take away is that these twisted theories depend on extra data, such as the spin C structures, in order to formulate the theory properly. And the analysis motivates the study of more general theories. Thank you.